In Chapter 11, our two standards are to explain and use volume formulas in three-dimensional figures, and then also to explain and find surface area in three-dimensional figures. This first section that we'll deal with in Section 1 of Chapter 11, we'll have our first lesson out of a few that will deal with really talking about the terms and also the formulas for volume. So we'll start with volume. So our objective for this lesson is I can find the volume of three-dimensional figures. So what I'd like to do is take a problem situation where one helicopter has a cylinder bucket to drop water on a fire and a second has a cone-shaped bucket to drop water on the fire. Which will complete the job faster and how much faster? Pause the video and then try this problem. See if you can answer those questions. So we are going to see how many of the cones can fit in the cylinder. I wonder how many you thought they could. We're going to start by pouring in one of the cones. Okay, so water is going to be poured in the cone. Okay, now we're going to try the second time. So we're going to pour in a second one here. Go ahead. Let's see how it goes. I hope I don't get wet. Oh. Okay, let's two of them fit in. Let's try a third one. Okay, so the cone pouring into the cylinder. Try it out. See if I'm going to get wet. If it's going to the third one. Notice the third one fills it up to the top. We're going to take a look at these figures that are three-dimensional figures, and we'll be using these quite a bit in the next section. We want to look at cubes, rectangular prisms, triangular prisms, cylinders, spheres, cones, and pyramids. And we'll talk about how we do the volume of it this section, and then we'll do surface area in the next one. So first of all, some terms that we have. If you have a prism and you're looking at what looks like a box, notice that the vertex of it, what we call that's really the corner of the box. We call it the vertex. We also have on the, we call an edge, which is the corner of where two of the sides meet together, and then a face is what one of the sides of the figure is. What we want to do is take a look at what would happen if we took that three-dimensional figure and we had it in a flat form. So if you take the flat form, we call it a net. And when you fold it, what would it look like? That's what nets are. They're three-dimensional figures folded flat, and then we want to talk about what they would look like when we actually fold them together. A net is just a flattened version of a three-dimensional figure. So if you take a figure like this and fold it up from its two-dimensional figure and make it into a three-dimensional figure, you get this prism. It's like a box, and when you unfold it, it looks like this, which is what's called its net. So this first example here is an example like that box that we have. If that box there, if we were to take it and fold it up, that folding it up would look like that figure. That's a box that's standing up. Now you've done in the past volume of figures like that. When we do volume, you just take the sides and multiply. So 6 times 2 times 3. If you multiply all those sides together, you get the volume, which in this case is 36. So what we want to do is talk about what these different three-dimensional figures are, and what their formulas are, and what their defining features of them are. So we're going to get some formulas listed here for our notes. So if you could take notes along with this, these are the formulas that we'll use. So we'll start with a prism, which are the ones that look kind of like a box, or different figures, like we've got hexagon bases or pentagon bases that we create boxes out of. So, but the first defining feature you need to know is that the base of it is a polygon. So we have those two bases, the parallel bases, are on the top and the bottom of the figure. So in this case, the polygon on the top and the bottom is, in the first one, is just a base with a square on the top and then also a square on the bottom. And then the second one that we have has instead, it has a hexagon on the top and then it has a hexagon also on the bottom. So those are the parallel bases that define it as being a prism. The volume for this will be the base area times the height. Now the base area, you have to calculate that. In this case, you'd find the area of either the square base or a hexagon base, whatever the base is, and then you take the area of that base and you multiply it by the height of the figure, however tall it is. So just base times height, kind of like what we had when we did the area of a rectangle or a parallelogram, if you recall. It was base times height, but in this case the base is a polygon. Pyramids are very similar. The base of it is a polygon, but the defining figure is, instead of it going up to another base, the edges come together and join at one point up at the top, or to make a pyramid. So for this type of thing, we have to make sure that we know how tall our figure is. So if we're dealing with a pyramid, we're going to draw the height in of it to see how tall it is, and that value we'll call h in this formula, just like we did for the other one. So the difference is, since this won't be as big as the volume of a prism, because notice it slants together, it always turns out to be 1/3 of the volume. It's kind of like what we did in that demonstration with the helicopters. We'll see that with the cylinders and cones too. Very common idea is that it's base times height, and then you multiply it by 1/3 for the pyramid. That base, that B, is still the area of the base at the bottom of the figure. Okay, so what we want to do is then move to, this was where you had polygons. What if we instead talked about having the base be a circle? So we're going to talk about these next two, cylinder and cones, and they're very similar in that their base is a circle. So the defining feature here is that you take that circle, and then you have still, just like we had with the prism, you have two parallel bases. In this case, they're parallel circles. One's at the top and one's at the bottom. So we'll see the diagram in just a second, but you can look at your note sheets, that figure of that cylinder there. Those bases are on the top and bottom for it, and I'll scroll up here just to show you in just a second so you can see it. But that volume then, for this figure, when we do it, is just like we had for the prism. The volume, in this case, because you have the same radius, both circles on both the top and the bottom, okay, the volume ends up being the base times the height, just like with the prism. In this case, though, the base is a circle, so instead of finding the area of, say, a square on the base for a prism, this time the base is a circle, and that base, if we multiply it by the height of the cylinder, we'll get the volume of the cylinder. And that's how tall the cylinder is for the height. So there we go. There's the diagram that you can see for this one. Now, the cone is very similar. On the cone, the base of the cone is also going to be a circle. But the defining feature, just like the pyramid, instead of having it two circles on the top and the bottom for bases like the cylinder, instead it's going to have the sides come together to a point, like it did on the pyramid. So a cone is very similar to the pyramid. This is kind of like this is the problem we did with the helicopters. So to find this volume, we need to know how tall the cone is. So we label the height of it as h. So this can be very similar to what we did with the pyramid. If you notice, our volume is going to be 1/3 of the base times the height, which is what we got for the pyramid as well. And that base times height was the formula for a cylinder, so it's 1/3 of that volume, just like we found out when we were talking about the helicopter problem before. So the base is the area of the circle base at the bottom. The height is how tall the cone is. Our volume is 1/3 times the base times the height. Now sphere is completely different. Its defining feature is just that it's a round figure, like a globe or whatever it is. It's a round figure in 3 dimensions. So when we do this type of problem, what we have to do is recognize that the formula is going to be different. On this, we have to worry about what the radius of that sphere is. So if you look at the sphere picture there, the radius, if we take 4/3 times pi and then cube the radius, because it's in 3 dimensions, we get the volume of the sphere. All right, let's go ahead and try some examples here. So if you take a look at these different formulas, we'll use them in different contexts. These are ones that you can hopefully have become more familiar with as you go along through the problems that we have in this chapter. So let's first of all classify these first 2 nets. I'd like you to pause the video and classify them. As you take a look at this first one, notice that as a square base, and if you fold up the sides, that will make it into a pyramid. So that one is a net, that's a square pyramid net. Now as we transition to the second one here, this net, if you notice, if you fold it up, it's got a square base to it. And as you fold it into a box, it's going to look like a cube. That's the more familiar way of referring to it. It's formally called a square prism, but it's folded up. It is in the shape of a cube. Now this last example, we'll do the volume of this cone here. And just as a reminder, when we do volume, you've got to do the area of the base first. And the area of that base is going to be a circle. So to do the circle, you're going to do pi times 3 squared, which is the base. And then when we do the base on this, we get 9 pi as our base. We're going to multiply it to get the volume by 1/3, because it's 1/3, just like we did in that demonstration of pouring the water. 3 of the cones fit into a cylinder, so it's 1/3 times the base times the height. So it's 1/3 times the 9 pi times 8, and that gives us a total of 24 pi.